Having discussed instrumentation systems in the last video, let's fill in a few gaps by briefly discussing sensors. The study of sensors could take a whole lecture course by itself, so I only intend to provide an overview here. However, you can use this video as a springboard to launch your own exploration in books and in other videos on YouTube. In this review, we'll classify sensors mainly according to how they respond to a change in their measurand. We can split them up into the following categories. Firstly, sensors which respond to a change in measurand by changing the voltage across their terminals. Secondly, sensors which respond by changing a current which is flowing through them. Thirdly, sensors which respond by changing their resistance. Fourthly, sensors which are simple switches. Fifthly, a broad category of sensors which change other more complex electrical parameters. And finally, number 6, smart sensors. So let's start our exploration with sensors which change their voltage. A good example of this type are thermocouples. These measure temperature and consist of two wires which are made from different materials joined at a point called the junction. Traditionally, there were 2 or 3 junctions, of which several were held at a known reference temperature and the other which was used to measure the temperature that we wanted to know. Nowadays, the effect of the reference junctions can be simulated electronically. The signal from sensors which change their voltage like this can generally be processed by simple amplification and, if necessary, by filtering. Now let's consider sensors which respond to a change of measurand by changing the current flowing through them. Good examples of these are photodiodes and phototransistors, both of which measure light. Phototransistors are sensitive, but photodiodes are fast. And in fact, photodiodes are used as a basis of fiber optic communication systems. For ease of processing in a circuit, the change of current in a sensor is changed into a change of voltage by a circuit called a transimpedance or transresistance amplifier. We'll see how to make such circuits later. Sensors which change their resistance are the most common type and include LDRs, which are light sensors, thermistors and RTDs, which are temperature sensors, and strain gauges, which measure strain, but can also be used with mechanical additions to measure load, pressure, and acceleration. There are 3 basic ways to alter the change of resistance into a change of voltage. The first way is to use a simple current source. As you know, this is a circuit which produces a constant current no matter what voltage is across it, and you can buy simple current sources in small packages. The diagram shows a sensor which changes its resistance by an amount delta R, and we can see from this that we can produce a corresponding change of voltage delta V, which is equal to I, the current from a current source, times delta R. A second way is to use a potential divider. In this circuit, the voltage out is given by the ratio of the fixed resistance to the resistance of the sensor. Both the preceding circuits, the one with the current source and the one with the potential divider, have a disadvantage that they don't produce a 0 volts output when a sensor is in its rest state. For example, if a light-dependent resistor or LDR was in darkness. This is because the sensor itself still has a resistance while it's in this state. So one final method is to use 2 potential dividers opposite each other. This configuration is called a Wheatstone bridge. Here, if all the resistances are the same, of the 3 fixed resistances and the sensor resistance in its resting state, then the voltages produced at V1 and V2 will be the same, and V out, the difference between those 2 voltages, will be equal to 0. The Wheatstone bridge has other advantages which we'll explore later, but one further one worth mentioning at this stage is that it's possible to use several sensors together by replacing the other fixed resistors, R1, R2 and R3 in the diagram, by one or more sensors, making the whole measurement much more sensitive. This brings us to our fourth category, sensors which are simple switches or produce a simple on-off signal. There are many types of these. For example, switches which detect whether a door is open or shut, or are attached to a float to indicate when water has reached a certain level, or are triggered each time a wheel turns round to count the number of revolutions. Such sensors can be attached directly to a computer without any further processing, and so they are perhaps the simplest of all types of sensor, and the easiest to use. Our fifth category of sensors is a sort of catch-all for sensors which don't neatly fit into any of the other categories, and there are a few of these sensors around. One example are piezoelectric sensors, which change their frequency when the measurand changes. Another are LVDTs, which change phase and amplitude and measure linear movement very accurately. Such sensors need their own specialized circuits to operate, and you can find examples of these in textbooks or in the sensor datasheets. Finally then, we must mention smart sensors. These are actually packages with both the sensor and its processing circuitry built in. Sometimes the circuit is just an amplifier, but they vary in complexity right up to examples which include an analog to digital converter and can plug directly into a computer, or even have wireless connectivity built in.